So this is my final exam for my algebra-based physics course. And so I think I wrote most of these questions, but in the past I would solve these all as different videos. I'm just going to do the whole thing. We're going to work through the whole thing. If you need to pause and go back and look at other stuff, that's fine. And it may be kind of hard to read, but that's fine. I'll read it for you. I have some extra paper. Oh, also I do give it doesn't really matter, but I do have an equation sheet. These are the equations I give the students, and I'll try to at least point these out when we get to them. So here's the first one, a penguin. There's the penguin right there, and I printed it in black because I hate my printer. That's a joke. I don't know why I printed it in black. So the penguin has a mass, let's call this MP of 11 kilograms. I'm just writing stuff down as I read it, and that's really a good idea to do, right? Kind of help you process what you're seeing and work through the problem. Walking on a board with a mass of 5 kilograms, so MB equals 5 kilograms. And also this would be the point where if you need to do any unit conversions, you could think about that or put down the units. I don't really do a lot of unit conversions in my problems. There are some, but not a lot because I really want to focus on the physics more. A length of 2.5 meters of uniform density. So right there I say, okay, that's 2.5 meters. I'll call that L. And that also tells me that the center of mass, since it's uniform density, the center of mass for the board is right there in the middle at L over 2. One end of the board is attached to a vertical wall, and the other end is supported by a wire at 50 degrees. So this is 50 degrees. If the wire can support 88 newtons, so this is like a tension force of 88 newtons, how far from the wall can the penguin walk before the wire breaks? So let's say this is X. So right there, I've kind of like processed the whole problem by writing down the stuff that I know and drawing it in a picture. But we're looking for that point at which the wire breaks. And so it's an equilibrium problem. We want to be up to the point, the maximum equilibrium, and then it breaks. We're going to use a tension of 88. If it's anything more than that, it breaks. But it may seem obvious that as this penguin moves, the net force isn't going to change. But what will change is the torque. So this tells us that it's an equilibrium problem. So I can say F net X equals 0, F net Y equals 0, and torque net O about some point O, and I get to pick the point as 0. And that's newtons, that's Newton meters, but that's fine. So let's pick the board as my object that I'm going to have in equilibrium. So here's my board, and now I'm going to draw all the forces acting on it and their locations. So I'll start off with the gravitational force at the center of mass. I'll call that MBG. The penguin pushes down on the board because the board pushes up on the penguin. And so if you said, oh, the penguin has a gravitational force right here of MPG, I would be okay with that. But that's wrong. Technically, that's not right. It's actually a normal force because the normal force pushes up on the penguin, so the penguin pushes down on the board. But since the penguin's at rest, the normal force of the penguin pushing down is the same as the weight of the penguin. I know it's me being picky, okay? But I'm just trying to tell you the truth. I want to always tell you the truth. Now I have this tension force right here. I'll call that T. And this is the angle. We'll just put that as theta right now. Now you know that I have to have, since there's a force pushing this way, part of the tension's pulling this way, there has to be a force pushing back that way. So I'll put it right there, F wall, and let's put this one right here as F wall. So the wall can push on it two ways. It can push on it this way and that way. Okay, so, and this is put down our values. I know that's the value X. This is the value L over 2. And this is the value L. Oops, sorry. So if I want to, I could write down, I'm going to go ahead and write these two equations down, even though it turns out you don't actually need them. So let's write down the net force in the X direction. Well, there's only two forces. There's the component of the tension, right, because this is the X component of the tension. And there's this FW. So I have FW, I guess I should call that 1. and this 2. FW1 minus t, that's a t, cosine theta equals 0. That's a t. So I know t, I know theta. I can actually find the force from the wall if I wanted to, but I just don't really need that. Now I'll do the same thing for the y direction. I have F wall 2, and then I have the y component of this plus t sine theta, and then I have minus mpg minus mbg equals 0. Now you'll notice here that I wrote these as vectors. That's actually a vector. But these are not vectors because this is the y component of the forces. The y component of this gravitational force is negative mbg. Okay, so again, I know t and know everything. I can solve for FW2. So this is an alternative way to solve the problem if you want to, okay? But we don't need that. We don't have enough here to solve for x because it's not even in the equation. But we do have x appear in our torque equation. So actually just go over here. Torque is on here. Torque equals RF sine theta. So R is the distance from the applied force to the point where we calculate the torque, and theta is the angle between R and F. Just so you know, I did give that equation. Okay, so let's pick a point to calculate the torque. If this is not rotating about the center of mass, it's also not rotating about that point. So I can pick wherever I want. If I pick this point, then I'm going to need to find FW2, which I can do. Okay, I'm not going to do it today, but it's possible to do that. And then FW1 will exert no torque because the R value for this is whatever that is, but the angle is 180 and the sine of 180 is 0. So that one won't appear on there, but that one would. But then the gravitational force would not. So the best answer here is to pick this as my point. Because if I pick that, I don't need to know what FW2 is, and I don't need to know what FW1 is. Both of those have 0 torque, so it doesn't matter what values they are. So if I pick that, I have torque net O equals, let's just go through. These are both 0 torques. This one is going to be the torque due to the penguin is going to be in the clockwise direction, so it'd be negative. So I'm going to say it's force negative mpg times its torque arm, x, times the sine of the angle between those, but it's 90 degrees, so don't have to worry about that. Okay, now what about the next force? It's this one. It's going to be the same thing. It's in the negative direction, so it's negative mbg, and its arm is L over 2. That's how far it is. And then finally, I have this force, and I'm going to go ahead and just use a perpendicular force, which would be this vertical component. So it's going to be plus t times, I did that again, plus t times L times the sine of theta. And all of those have to be equal to 0. And what do I want to solve for? I want to solve for x. So let's move these, let's add this to the other side, subtract that, and I get, well, I guess I could just add this to the other side. So I get mpgx equals TL sine theta minus mbg L over 2. And then I divide by mg, and I get x equals TL sine theta minus mbg L over 2, all of that over mpg. Let's put in my values. So I know t is 88. This is going to be 2.5. Sine of 50. I'm going to run out of room. This is all on the top. Minus mb, which is 5, times 9.8 times 2.5 over 2. All of that over 11 times 9.8. You can't cancel those g's, right? I can't cancel those because they're in different terms. But I can go ahead and put this in my calculator, even though I don't want to. I want to do this in Python. But I'm going to do it in my calculator. So parentheses 88 times 2.5 times sine of 50, close parentheses, minus 5 times 9.8 9.8 times 2.5 times 0.5. I like to do times 0.5 instead of divided by 2. Close parentheses divided by, open parentheses, 11 times 9.8 close parentheses equals. I get 0.995 meters. And so you want to check here, is that a reasonable value? I mean, it's not disreasonable, right? If it was, could it be greater than 2.5? I mean, it could be. I could have made a bad problem. In fact, I wrote this problem and I picked the value of the penguin to be 1 meter, and then I solved what the tension would need to be, and then I gave you the tension. So that's why that's close to 1 meter. The end. Next problem. So in this test, it doesn't really matter for you because you're just a viewer. But in this test, what I did was I gave them they only had an hour and a half. So I gave them 5 problems and they could pick 4. So some of these problems are actually easy, some are not easy. But that way they can pick whichever ones they feel comfortable with. So here is a block of mass 200 grams. So let's call that M1. M1 equals 200 grams equals, I'll go ahead and convert this in my head, 0.2 kilograms. You don't have to do that. Sits on a frictionless inclined plane 37 degrees. I think I actually made that triangle 37 degrees, but I can't remember because I did draw that picture. The block has a string connected to it to run the plane, and it's connected to a 200 gram block on the edge. So these are both the same mass. M2 equals 0.2 kilograms. I thought that'd be fun. What is the tension in the string once the blocks are released from the So I'll take this and I'm like, oh, what's going to happen? Well, they're going to accelerate if it's frictionless. But the key thing here is that the tension, since we have one string, the tension on this block has to be the tension on that block, even though they're in different directions. And the acceleration of this block has to be the acceleration of that block. So we get 2 Newton's second law problems. Let's write down this one. So I have here my block. What forces do I have acting on that? I have the gravitational force, M. I'm just going to call it M. There's only one M. mg. Then I have the normal force, N. And I have the tension. And in this case, these are vectors. And in this case, I'm going to call this the x direction, and that the y. And in that case, this angle is theta. So let's write down the net force in the x direction. So I'm going to say F net x. It's going to be T, right? There's the tension pulling in the x direction. And then I have a component of the gravitational force. It would be the opposite side of that right triangle. So it'd be minus mg sine theta. And I can't solve for t because I don't know the acceleration. And this is equal to ma. So I'm assuming it's accelerating up the plane. That's just an assumption. It doesn't really matter. If you're wrong, you're wrong. It's fine. But that's the equation. I don't know t and I don't know a, so I can't solve for this problem. Well, let's go to this block right here. So here's that block, and it has a tension pulling up and a gravitational force pulling down. And the mistake that I would have made as a, how old was I when I took physics? I don't know, 19 or 18-year-old human being. I would have said, oh, those are equal. They're not equal. Okay, so let's draw the, write down Newton's second law for this in the y direction. I'm going to call that the y direction. There is no x. I didn't need the normal force here, so I didn't even bother with that. I would need that if there was a friction, but there was no friction. So here I have F net y equals t minus mg equals, now, if this is accelerating this way, this one has to accelerate that way. The string has to stay the same length, so they have to have the same kind of direction. So this is going to be minus ma. If I want to have the same value of acceleration, I need that negative sign right there. But now I have 2 equations and 2 unknowns. I don't know a and I don't know t. Let's solve this one for a. So I get, if I divide both sides by m, I get a equals t over, that's a parentheses, over m minus g sine theta. The masses cancel. Now I'm going to plug that in down here and solve for t. So I get t equals mg minus ma. Now I'm going to put in my value for a. I get T equals mg minus m, and then a is going to be T over m minus g sine theta. Is that right? Okay, so then if I multiply the m through, I get T equals mg minus T minus mg sine theta. Now I can add t to both sides, and I get 2t equals mg times 1 minus sine theta. Right? Both of these terms have an mg, so I factored out the mg. You don't have to do that. And then I divide by 2. I get t equals mg 1 minus sine theta. All of that over 2. Now I can put my values in. I have 0.2 times 1 minus sine of 37. All of that over, I missed my g. 9.8. All of that over 2. So if I put that into my handy dandy calculator here, right there, how's that? Okay, clear 0.2 times parentheses 1 minus sine 37. And notice I'm in degrees mode here. That's good. Times 9.8 divided by 2 equals, I get 0.39 newtons. I think that's the right answer. Yep. I'm always questioning when I put in numbers in my calculator because I hate calculators. Okay, so I mean, this was probably maybe the second hardest problem. But it's not too hard. I mean, the only problem is that we have to draw force diagrams for two objects and then say they have the same tension and the same acceleration. That makes it a little bit more complicated, but I thought it was fair. Of course, I think all these questions are fair because I'm biased, and that's okay. This is the hardest question, okay? But I like it. Tarzan is king of the jungle. That's not a question. That's just a fact, okay? And has a mass of 100 kilograms. You know, I figured he's kind of a little bit beefier than a normal human, or me. He's king of the jungle, right? And he decides to swing on a 3.8 meter long vine. He starts the swing from rest at a 62 degree angle from the vertical. What is the maximum tension? So let's draw this. Maximum tension. It's actually a two-part problem. That's why I like this. So here's a tree or something. Here's a vertical. Not to scale. And that's theta. And this is L. It's going to swing down here. And so the question is, where is the tension going to be the greatest? The tension is going to be the greatest at this bottom point. Because at the bottom point, I have the following forces. I have the gravitational force, mg, and I have the tension. But those are not equal, because if he's moving with some velocity, then he is accelerating. He's accelerating because he's moving in a circle. And the magnitude of that acceleration, AC, is going to be v squared over r. That's the acceleration direction. So let's go ahead and write this down. So let's say F net y equals t minus mg equals m v squared over r. But the radius of the circle is actually just L. So I want to find t. I know m, I know g, I know m, I know L, but I don't know v. All right, that's the question. So if he goes down here, how fast is he going? So this is actually the second part of the problem. The first part of the problem is to find the velocity. So in this case, I'll use work energy because I'm dealing with a change in position. So I can say my system is king of the jungle, plus the Earth. In that case, I only have one force that could possibly do work on him, because I'm going to say work is a change in kinetic energy plus the change in gravitational potential energy. And I have gravitational potential energy because of the Earth. And so then K is 1/2 mv squared. U is mgy on the surface of the Earth. And I did give these just so you know. Work is a change in energy. K is 1/2 mv squared. Ug is mgy. What fell? Okay. So the work. So that I only have two forces acting on them, and gravity does not do work on the system because it's part of the system. And the tension also does not do work because at every instance, the tension and delta R are perpendicular. So work is F delta R cosine theta. But if theta is always 90 degrees, the tension does no work. The tension only changes his direction. It doesn't speed him up. So that's 0. So this we'll call position 1, position 2. So I have 0 equals K2 minus K1 plus U2 minus U1. So in this case, the initial kinetic energy is going to be 0 because he starts from rest. Now what about U2 and U1? Here I have a choice. I can pick where y is equal to 0. And just to make it easy, I'm going to pick y equals 0 down here. So that means that U2 is 0. Now I get 0 equals 1/2 m v. I'm just going to call it v because the velocity up here was 0 and I want to match with this. V squared minus 0 plus mgy2 y1. I mean, that's minus mgy y1. I forgot. Now, I don't know y1, though. Okay, so now we have to do a little geometry. If this is 0, then this is a distance L. That whole thing is L, right? Because it's part of a circle. This is the side of that. So this is going to be L cosine theta. So this to here is L. Here to there is L cosine theta. So that means that y1 is going to be L minus L cosine theta, or L times 1 minus cosine theta. That's this little piece right here. That's a little trick. I get it. That's a little geometry trick, but we did that in class, so I feel justified in putting it in there. Or you could not do the problem, right? Because I gave you one to drop. So if I put that in here and solve for v, I'm going to add that to both sides. I get 1/2 m v squared equals mgy, which is going to be L times 1 minus cosine theta. The mass cancels. I can multiply by 2. I get v squared equals 2gl 1 minus cosine squared theta. And I'm not going to solve for v because I don't care about v. I need v squared up here. So I already have v squared. If I take the square root and square it, that's no fun. So if I solve this for t, I get t equals m. I'm just going to add mg to both sides. Mg plus m v squared over L. So the v squared is going to be 2gl 1 minus cosine theta over L, and the L's cancel, which I'm actually a little surprised at, but I want to think about that more. I think if you have a smaller length, then you're not going as fast, but you're accelerating greater. So because you're turning harder in a circle. So it seems kind of funny that it doesn't depend on the length, but I don't know. Okay. So now I know everything. I can find my value of t. That was a goal. So let's put in my values. T equals m 100 times g 9.8 plus 100 times 2 times g times 1 minus cosine of 62. All of that over nothing because it's divided by L. Okay, so let's put it in my handy dandy calculator. That is from Blue's Clues, you know, my handy dandy notebook. Yeah, I never watched it myself, but you know my kids watch it, so I remember it. Okay, so I'm gonna put in, this is 980, right? 100 times 9.8, 980 plus, this is 980 again, 980 times 2 times parentheses 1 minus cosine 62 close parentheses equals. I get 2019.8 newtons. I think that's a little bit different than what I got before, so I feel like there's an error somewhere in one of my two answers. I actually solved this before. But if t minus, I think that's okay. mv squared over r. Yeah. I'm going to go with it. And let's just compare. I mean, it's greater than the weight, which it should be, because the weight would be 980. So it's greater than that. I think this looks okay. Okay, we got two more problems. Okay, this one is not easy, but it looks hard, and there's a typo here. This is 8. I did correct that in class. So during a new moon, the moon is mostly in line between the sun and the earth. So we have here the sun, the moon, the earth. And I give the mass of the sun, the mass of the earth, the mass of the moon, the earth-sun distance. So this we'll call RSE. The earth-moon distance is, let's call that REM. That's it. And so the question is, which pulls greater on the moon, the earth or the sun? So we know that there is the magnitude of the gravitational force, I call it Fg, between any two objects with mass, m1, m2 over r squared. So it's the product of their masses divided by the distance between them squared. So here I have the distance from the earth to in this position, the sun to the moon, we'll call that RSM, is equal to the distance from the sun to the earth, RSE, minus this other distance, REM. Now, if you just used, if you put the earth and the moon at the same distance for the gravitational interaction with the sun, you get a fine answer, because this is really small compared to this, so that's fine. So we're calculating the force on the moon, so I can say Fs, that's the gravitational force due to the sun. It's going to be G times the mass of the sun times the mass of the moon divided by this RSM squared. So they're just numbers. All I have to do is put in the numbers. Now, it is scientific notation, and I'm not going to do this in the calculator because it's boring. And then the gravitational force due to the Earth, Fe, is going to be G times mass of the Earth, mass of the moon, over the distance between those two squared, which is REM squared. So I want to calculate these and find out which is greater. That's all. Okay. I'm switching to Python for this one because it's just no fun doing this scientific notation. So let's put my values. I have, can you see this? So G equals 6.67 times 10 to the negative 11th. Yes, I do let my students use Python if they want. They got to show me, though. So it's an option. And I have, let's see, RSE. Let's put the masses. MS is the mass of the sun. 1.989 times 10 to the 30th. Mass of the earth is 5.972 times 10 to the 24. Mass of the moon is 7.35 times 10 to the 22, right? And then I have RSE is the sun-earth distance, which is 1 AU, and that is 1.496 times 10 to the 11th, and then REM is 3.844 times 10 to the 8th. And then I can get RMS, what did I call it? RSM is RSE minus REM. This what's really nice about using Python is that I don't even actually need to know that number, right? I just have a variable for it. Python knows, so I don't need to know. Fs equals G times MS times MM divided by RSM squared. Squared in Python star star. Print Fs equals Fs, and I'll put the units because I gotta be proper. And then Fe is going to be G times M, times Me times MM divided by REM squared. Print Fe equals Fe newtons. And run it. So which one's greater? That's it. And the answer is the sun. The sun pulls more on the moon than the earth. And it's one of those fun things, right? Why does the moon orbit the earth rather than the sun if the sun pulls greater on it? And the answer is it doesn't. It actually does orbit the sun. It orbits both the earth and the moon. It's a more complicated problem like that. But I think a lot of people think, oh, the moon is pulled on more by the earth and is attracted to the earth. It's not necessarily true. Okay, so that was pretty easy. I think that was the easiest question in the test. But it's a little intimidating. It's deceptively easy because people see all these numbers and say, oh, crap, I don't know what I'm going to do. But if you just stick to it and you use your calculator and you use scientific notation, correct order of operations, you'll get it. And on top of that, if you show your work and you put in your numbers here and you make a mistake, I'm not going to be that bad. Oh, this is a good one too. This one, let's go ahead and solve it. So, I have a car. So here's my car going around a circle on a road, and in that case, if it's moving in a circle? Then there has to be a force pushing towards the center of the circle, and what force is that? It's the frictional force. So let's draw the car coming straight towards us. So here's the center of the radius of curvature for this on-ramp. And here's my car. It's coming out, so it's like this. So I have the gravitational, I'll draw it over here. So I have the gravitational force pulling down, mg. I have the normal force pushing up, N, and then I have the frictional force pushing this way, sideways. And that's what makes it move in a circle. So let's call this the x direction, the y direction, and then I can write down everything I know. So I can say F net y is going to be N minus mg equals 0. It's 0 because the car is not accelerating up or down in the y direction. And then I can write the same thing for the x direction, F net x. Well, what forces are acting in the x direction? It's just this frictional force. So it's going to be negative frictional force, and that's going to be equal to max. At that instant, what is the acceleration? Well, the acceleration is in the negative x direction, and it has a value of AC equals v squared over r. Because that's the centripetal acceleration, that's the velocity, and that's the radius of the circle. And it's negative because that's towards the center of the circle. I drew it this way. I just picked it on the right. And in my version, it's pushing to the left. So I have, this is negative frictional force equals negative m v squared over r. Now, what am I trying to find here? It says if the road has a radius of r equals 25 meters, the coefficient of static friction is mu equals 0.5, and then m equals 5,000. I'll do this first car first. If it's just barely making the turn, then we're using maximum friction force. Normally, I'd say the friction force is less than or equal to the coefficient of static friction times the normal force for static friction. But we want to know how fast it can go, so that we're using maximum friction. So we're going to say this is equal to the coefficient of friction times the normal force. But that means that I need to find the normal force. Well, I can get that up here. If I solve this for n, I get n equals mg, because I just add mg to both sides. So now I put that over here, and I get mu s mg. Now I can put that over here. The negative signs cancel. I get mu s mg equals m v squared over r. And I want to solve for v. So let's multiply both sides by r and divide by m, which cancels. And I get v squared equals mu s g r. And then v equals the square root of mu s g r. Now you'll notice the first thing I asked about cars and trucks. The mass canceled, right? Because a truck is going to have a greater mass, so it needs a greater force accelerating it, but it's going to have a greater friction force because it pushes down harder on the road. So those two things cancel. Also over here I have G in meters per second squared times R in meters. I get meters squared per second squared. The coefficient is just a coefficient without any units. So if I have the square root of meters squared per second squared, then I get meters per second. So the units do work. Also, if I increase the friction force, I get a greater speed. If I increase the radius of curvature, I get a greater speed. So if you want to go really fast around a curve, you want a bigger curve. But let's go ahead and find this value of V. V equals the square root of 0.5 times 9.8 times 25. And I get, handy dandy calculator, clear, square root 0.5 times 9.8 times 25 equals 11.07 meters per second. And then if we look, just really quick over here, I can't remember the value, 1 meter per second in mile per hour. So if I multiply this by 2.24 miles per hour divided by 1 meter per second. I didn't ask you to do this, okay? I'm just doing it for you. Then the meters per second, this is a value, these are equivalent values. So I'm multiplying this by the value of 1. So I'm not changing the answer. I'm changing the numerical value, but also the units. So the meters per second cancels, and I just take that number and I multiply by 2.24 equals. I get 25 miles per hour. That's how fast you can go. If you go faster than that, if that's your coefficient of friction, you'll slide off. Now, there's the fun problem of what if there's friction? I mean, what if it's a banked curve? Then in that case, this normal force is that way. And so you have part of the normal force pushes towards the direction of the center of the circle. And the friction force actually is this way too. So that's partly too. But the faster you go, the greater the normal force because you push into that thing more. So banked curves are better, but it's more complicated to solve. So there is your physics exam final and the answers. Hopefully you found that useful. Yeah, there you go.